Hello, this is Kevin, and I'm going to be presenting our slideshow for our Master's Wireless Security project that we will be using at the current point. The final presentation will be based off of this project, but cleaned up towards the end to improve things such as proper code quality, improving integration of all tools being used, and to provide a more smooth user interface rather than just a pure text terminal interface that we're currently utilizing with the goal of making it a better user experience overall. For now, we'll be presenting our project as is, with the tools working as intended and returning the results we expect to give us proper security information. The purpose of this project is to address any security concerns someone may have when connecting to a wireless network. Many times when accessing public wireless networks, which this is the primary use case for our software, people will be unsure of how secure it is. Is it safe to connect to? Is it someplace they need to worry about? Is someone accessing their data improperly? What do they have to worry about? What should they be concerned with, and what networks are safe to connect to? While there is no way to make sure everything's properly in place without training and a lot of work behind it, we can at the very least ensure that their network does not have the certain key issues that we would expect from an improperly secured wireless network, such as being a rogue access point, evil twin, or just a network access point that a malicious actor could connect to themselves as a third party. To go over how our software is going to work overall, automation is key. The user should have to do very little other than press that they wish the program to run, and in some cases may have to enter in or reconnect to the network one last time after completion as a means of ensuring that's actually as safe as they need it to be. Otherwise, it is just a simple case of it running automatically using shell commands to do all the network tests that are needed without any need for the user to need to input additional data as they go on. So once connected to a network that you're curious as to how security is, it'll start running the checks one by one and alert the user of any issues as they arise. Afterwards, the user will be able to decide if it is something they wish to go forward with or if they want to decide to disconnect and use another form of access point connection. As we run, the program will work by executing shell commands using tools such as the subprocess toolset module, and by doing so, the system can work very universally between multiple different programs, provided it is on an operating system, Windows or Linux, that our program is designed for. The program will also automatically check for that as well, reducing the need for user input and greatly expanding the number of devices our software can be used on as a form of security testing. The first test is that one, by the way. It is to check if it is on a Windows or Linux Linux system overall. By running different shell commands, we will be able to see immediately what the output is. Either the shell command for a Linux output, the current default our system is designed for, will check and return what's expected that a Linux system is detected, or that command will not work and the process to check for a Windows one will run. Otherwise, it will return that there is not a known OS that the software is being used on, and it won't be able to run the program whatsoever. But that should only occur if attempt to run on a Mac device or on an operating system that is not even listed, such as Linux, that is not expected. These are designed for an Ubuntu-based Linux system at the time, though we expect it to work on many other types of Linux systems, provided it does not require unique shell commands or have unneeded restrictions on what the user is able to access through the terminal under normal systems. At no point do we require any sort of things that would require too much access. It is just going to be normal, quick checks as to what the network is and what you are inputting into it and what you are connected to already. To go into the important test, the first test does not actually matter what operating system we have. Thankfully, as it only needs to run the same software and same types of terminal shell commands for both the Windows command line and the Linux terminal, we can use the same software to check both types of operating systems, saving our code base Here, what we do is we find the output of the ARP table and clone it into a text table that we can then search. Here, we check all of the available MAC addresses that are available to your device and see if there are duplicates. Duplicate MAC addresses can be indicative of there being a device pretending to be the address of a different one, so that when someone tries to connect to it, they send the packages to a device that's not meant to be that one. By hiding their address with a different one, it could be trying to steal data or pretend to be something you don't want and then push that data forward. When, if that is the network you're connecting to, that's something you're greatly concerned for. And here we're just going to return if you do or do not have duplicate MAC addresses. Moving forward, we're going to check the routing that your packages will take between you and the network by checking the IP address and then running to the trace between you and the device, seeing both differences between Windows and Linux for the slight differences in the routing, such as Linux systems using the IP route commands, while Linux being able to use ipconfig to run the check, for example, and then the trace route versus tracert for Linux and Windows respectively. We can then check if there is a device between you and the network you are trying to connect to. As you're connecting to the specific IP address of the network, you should not have anything between you and that router, that network device, in most instances. There are specific times where you may expect that, such as with Wi-Fi extenders, it is possible, but those are going to be rare occurrences, especially rare to have them listed as their own individual network that you are hopping between. If you've never seen this before, you would use similar trace checks to test to connect to a Google server and see how it would go through. We are using this to connect to our own network and see if there's a device between us and them. And it to check as another way of checking for a man in the middle that could be between you and the network and steal your data. Finally, we check the encryption of the network you're connecting to. Again, separate for Windows and Linux. Windows to the left, Linux to the bottom right here. And here we can see that different security protocols are very important. The encryption your network's using. Most networks are going to use something like a WPA2 or 3 encryption protocol, and that's going to be perfectly satisfactory, while other systems such as WEP have been broken for quite some time, being static based and instead of being dynamic, mean that they are not safe to connect to. It being WP does not necessarily mean that it is a malicious network, but it could mean that a third party is connecting to it and is not and may gain access to everything on that network, including your device, whether or not the people running that network they themselves are malicious. Otherwise, it can also check if there's no password requirement, which that itself is something to be concerned of. Thankfully, if there's no password requirement, it will automatically skip our following password test for passwords, meaning it will save operating time instead of trying to run the same checks on something that just does not exist. Running our password test, we check to see what the password requirement if it is accepting fake passwords. By doing many malicious networks will pretend to be secure by having password requirements when really anything you enter it will accept as a password. This may be done to either make you get a false sense of security by thinking, oh, this network is good, connect to it's okay, or is trying to steal your password to that network, such as if you know to connect to a access point using a very specific password designed for just you or the people that are allowed to connect to it, but it wants to connect to it maliciously. It will ask you to enter. It will have you enter in a password for this fake connection, allowing to not only potentially steal a password from you, but fake its security credentials, making it look more legitimate than it actually is. Here we do multiple different types of checks depending on if it is a Linux or Windows system, where we can see what sort of password requirements are there in the first place, or inject a fake password to try and test its quality. And from after this, we'll run through the Linux execution of this software, followed by the Windows, to go through the details and differences between each. Thank you. Here we will go through an example of our master's project for Wi-Fi security testing utilizing a Linux operating system. As you can see, our system first executes everything through our main file that then goes through all of our testing files to give the output at each point. By doing this, it allows us to very easily connect our main to any new tests that need to be done, dividing them out properly by operating system through our checks, and just importing them in, saving any currently unused or currently being tested programs in a hold folder for safety and to avoid unnecessary deletion without adding them to the main or causing unnecessary confusion. To go through how it would work, first we run our OS AB check, which is an AB test, returns a binary that tells us which operating system we have. To go through our OS check, it runs a subprocess to inject first it assumes Linux is the system being used and tries to run a command check through the shell terminal to see what the output is. We run this as a shell to capture the output in the text and strip off any unnecessary. First, checking if it even contains the text Linux. If it doesn't contain the text, either that means it is a different operating system or the uname check does not work due to it not being Linux. Either way, if it is found, we return true and exit out of here, knowing that our check OS AB is going to be true, allowing us to run Linux checks. Otherwise, we would run the check for Windows, running the subprocess for var to see which operating system it is, seeing if that returns Windows. If that doesn't return, we know it is some sort of unknown operating system, or it does not work in the way our system is programmed to be able to. We're telling the user that is an unknown US and exiting the program entirely, unable to do any checks. From there, knowing that in this system we are running Linux, we can start running through the next tests. Our first one is to check the MAC addresses by checking the ARP table. This is the same for both Linux and Windows devices, so we do not need to duplicate the code, allowing for a more simple execution. Going through here, it runs the check ARP and then goes through everything above sequentially by saving the ARP to a table and then iterating through the table, checking for pairs and saving any duplicates. And if any are found, we returned to the user that there were duplicate MAC addresses found, which could indicate a malicious device on the network. Otherwise, it'll return that there are no duplicates found and proceed as always. From there, we run into the Linux specific tests, where we check for the truth of the operating system AB test is true, indicating Linux. First, we are checking the number of hops to the router. Doing this is the way is stated earlier, the means of checking to see if there is any sort of malicious device between you and the network. Like the others, we are checking the routing to see how many route points there are between us and the device we are connected to. By first, we find the IP address, and then we check the routing between your device and the IP address itself. By doing this, we'll know that between us and the IP, or the router we're connected to, we'll see any points between us and them that are trying to hide themselves, and letting the user if there is more than one connection point. After this, we check the encryption protocol. This, however, also returns a true-false check, as if there is no encryption, it'll run a different test. If there is encryption, it will run a password test. Well, if there is no encryption, that means there is no real password requirement, meaning there's no need to test the test for a password itself, knowing that there is not one there. The test, like the other, checks the network security checks, dividing out only the necessary devices and seeing the return output. From there, we will see what is being returned. We will return and be able to see what sort of security there is. In many cases, this will be some sort of WPA network connection in secure systems, or a WP connection, security connection, which would be an improper security feature, but it would mean it is there in the first place. It's something to be concerned about, but at a different level than something fake altogether. Return the output. Now, assuming we do have a password requirement of some kind, it then runs our check to run the password test. What we do is we get the name of the network, and then try to connect to it directly through a shell command. Here though, we inject a fake password, this test1234 exclamation point. It's set up this way to allow for most what some networks may say up as false requirements, like how many legitimate networks will require an uppercase letter, number, special characters, while also not being a realistic password in most cases. If this password actually works, that's also a security issue of having an improper password, but different than the ones we are looking for. If this allows you, oddly enough, if this allows you to connect to a network, it will it will be more dangerous than if it doesn't. And something we are expecting in this output is on any secure network is that this will prompt you to either need to reconnect manually or fail entirely. Below here, for our own use, we have saved the output codes that are going to be printed to tell us what we are finding. A success of 0 is something we do not want to have. On a Linux system, we expect it to prompt us to enter the password if the password being injected here is incorrect. And so here, if it runs and prompts me for a password, I'll know my system is actually secure. While if it does connect without needing a new password being tested, that means my own system, my home Wi-Fi, is set up for a poor test, to accept fake or very poor passwords. And now we can simply run through it and see the output. First of all, we can see it's a Linux system, and it quickly checks that, and it checks everything. And before I can even finish talking about it, the test is run through to the final one. This is something we really want for our users so that way they can have a very fast reaction, and simply running the program tells them exactly what they need. Here, I see that as fake, and the password did not work. If I had clicked on that, we would have seen the fake, and now I can enter in my real password, allowing me to actually connect. And we have this output code of one code telling us it did not have a normal success. And I probably typed that in wrong. And from there, we are able to know that it did not successfully connect with a fake password. We had a normal protocol of the WPA2 encryption. There's only one connection hop, meaning there's no one between us. The ARP check passed, so there's no duplicate MAC addresses, so no one's trying to manipulate my network or pretend to be it. And as I am on a Linux operating system. All of these combined are good to tell us that the system is safe, and now we can proceed to test this on a Windows operating system.